Hi, I'm Frank Dellaert, and I'm happy to present work by my former PhD student, Ye Tong. He's now in the motion planning team at Waymo, and his work is on using manifold optimization for constrained problems. When you model a robot, you often resort to generalized coordinates, and if you have an arm where there is not a lot of constraints, it's all free, that's quite easy. Things become a little bit more messy when you have parallel robots or you have contact. Then it's not so easy to formulate those constraints in generalized coordinates. You can do analytic work and you can try to find a formulation, but it becomes really a handcrafted task. Using factor graphs and using the formulation from Lynch and Park with modern manifold-based representations of the dynamics, you can create a factor graph-based representation of the dynamics and the kinematics of your robot system. And in these sort of total coordinates, it's quite easy to add arbitrary constraints. Okay, but you get a larger problem to solve. So our solution is to use manifold optimization. So manifold optimization has a long history in robotics, starting with Rock. And it's a recent text, notably the book by Apsel and Balker and Mahoney, the amazing book. GTSAM, which is a library that we built at Georgia Tech, has been a manifold optimization library from the start. There's many others. And there's a really nice book on manifold optimization from Bumo, which is more recent, which concentrates on submanifolds. And so our idea is if you have a complex factor graph that represents the dynamics of your robot, maybe over time with a bunch of constraints, you can actually identify connected components of variables and constraints. And out of these connected components, you can create on the fly new manifold variables. And these manifold variables, right, if you have, say, 2 6-degree of freedom poses and 1 range constraint, instead of a 12-dimensional set of variables, you now have an 11-dimensional manifold, which is a constrained manifold. So you can create these so-called super variables. They're constrained manifold variables. And we simply do manifold optimization, which is an unconstrained optimization problem on this new factor graph with manifold variables. That is actually the idea of Ye Tong's 2023 paper at ICRA. Here is the example for a hemodynamic motion planning problem. And you can see that there's these connected components of constraints. And then the time slices of this motion planning problem are connected with soft constraints over time. In 2023, we showed that this leads to very fast, low-dimensional optimization problems, unconstrained, because you now have these manifold variables that satisfy your constraints. And the feasibility, the constraints are actually satisfied almost exactly by design, by construction. What we did not do is inequality constraints. So this was all equality constraints like kinematics, multiple links connected using joints and things like that. So Ye Tong came up with a second paradigm, which is, and this is a paradigm that's known in manifold optimization. It's called manifold with corners or boundaries. So that is, if your manifold is sliced using inequalities, you get a manifold that has boundaries where you can't get past, right? And if several boundaries intersect, you have a corner. So the whole concept is called manifold with corners. And here are some examples, but in the poster, I'll happily talk about the details in more detail. What you get is a bi-level optimization, really. At the top, you have a manifold optimization problem. It's unconstrained. You don't have to care about constraints. The constraints are all implemented by calculating and constructing tangent spaces on the fly and doing retraction. So the retraction is a process of if you leave the manifold to go back to the manifold. Because you have a sparse factor graph, and the sparsity is preserved with the manifold variables, we can do the retraction in parallel and very quickly, right? The retraction itself, you can do in a first-order way or in a second-order way. So this is basically a projected grade, or you can do a second-order Livermore-Marquardt style for each of these manifold variables. So that's the bi-level step. At the top, you have unconstrained optimization. But all the little manifold retractions are small optimization problems, but with the emphasis on small in themselves. Right? We have in the paper three examples. One is a simple sort of ant planning problem. We do estimation. We have cart ball with friction, and we have a complex multi-phase hybrid collocation system with a quadruped jumping over a barrier. This is an example of that quadruped example. All the constraints are satisfied. This is a fairly complex. At the original level, it's tens of thousands of variables, but when we switch to manifold variables, it becomes maybe 1,000, right? And we beat all other optimization problems that are classical constraint optimization methods. There is a deep connection with existing classical constraint optimization methods. And again, at Poser, I'll love to sort of talk to you and get your perspective on this new way of thinking, which is manifolds with corner. I have two posters in the back that I'll talk about, one with Frederica and Avinash, and then the one that I'll be manning because Yitong unfortunately couldn't travel here because of visa issues, etc. So thank you very much. I'll see you in the back corner over there.